All right, so 12.9 is on Taylor series, and so depending on how much time you spent, I guess it was maybe even back all the way in Calc 1, they might have talked about Taylor polynomials. Taylor polynomials were an extension of the idea of the linearization. We'll touch on that at the end of this section, but for the most part, we're going to just stick with Taylor series. And so we're going to come up with the Taylor series formula here in a second. And so the idea is still the same thing. We want to represent functions using infinite series. Okay? And so this time we're going to start, so in the last section we started with the series that we knew for the geometric sum, right? The 1 over 1 minus x. And then we manipulated that to find new series. In this section, we're going to start with functions and say, okay, let's hope we can find a series for that function. And if we start with a function, what's that series have to look like? Okay? And so let's just, and this is really the Maclaurin series. I'm going to just say Taylor series and then tweak it as we need to. Okay, and we won't work all the details out, but in general, this is what power series look like if they're centered around 0, right? Hopefully that'll be enough. Okay, if we got a power series centered around 0, it should look like that, right? And again, not every function actually has a power series, but we're assuming, suppose a function has a power series, and even if it has one, it may not work for all x, like 1 over 1 minus x, right? It's defined as long as your x is less than 1. Otherwise, you don't have a nice series for it. Okay, so our goal is to suppose in this situation we're given this f, right? And we want to come up with an appropriate series that represents it. And so we just need to figure out what these c's will equal. Does that make sense? So some of them are really easy. What's f of 0?
C0.
C of 0, right?
Okay.
Because that one has no x, so it's c of 0. And so that's what c of 0, no matter what you get, has to be your f of 0. Does that make sense? Again, we're under the assumption here that this series actually exists. And so that means we should be able to take, and it exists at some places other than just 0, right? Remember, series, this thing's always going to be defined at 0. If it's at all of any interest, then it's defined on some interval around 0. So we're assuming we're in that situation. What's the derivative of that function, of the power series side? C1, C2, C2, x. Oh, x cubed. And 5. And so on, right? So what if I plug in 0 to this derivative? What do I get? C1. So again, our C1, if we're going to have a series that represents a function, the C1 has to be the derivative of that function. Does that make sense? And so it should be pretty clear that's how this formula is going to work, right? It's going to involve the subsequent derivatives of a given function, but they get a little messier than that. It's not just that C2 is the second derivative and C3 is the third derivative. It's a little bit uglier, but not much. So what's the second derivative of your function? C2, C2, right?
No, only 2.
What's that?
The derivative of 2c2.
So the derivative of, the second derivative of C1 is 0, right?
Okay.
And then it's 2c2 times x, so that's
Okay.
the derivative, right?
No.
And then here, the 3 stays there,
6.
the 2 falls down, so it's 6, but let's write it as 3 times 2, C3, now x, right? And then 4 times 3, C4, x squared, 5 times 4, C5, x cubed. Let me get rid of this other stuff here. Does that make sense so far? And so you can probably, or might be able to start guessing the answer, but let's just slowly work our way through it. So the second derivative at 0 is what? 2c2. So again, we're under the assumption that we know f, we want to find the c's, right? And so we're thinking of this has to be true, so our c2 must be the second derivative over 2. Does that make sense? Again, you might guess a formula now, but be careful. Let's work out maybe one or two more. Third derivative is going to be what?
6c3.
Okay, and let's not count, let's make it 3 times 2c3, right? That's fine. And then 4 times 3 times 2 c4x, right? And then 5 times 4 times 3 c5 x squared, and so on. So same idea here. Third derivative at 0 is 3 times 2c3, right? So your c3 is your third derivative over 3 times 2. And so maybe I'll stop here. If you don't see it, that's okay. Let's talk about it. The nth derivative is going to be what? It's going to have c sub n. What's going to be in front of it, though?
And the factorial.
Yeah, n factorial, right? Because it's, for the next one, it'll be 4, 3, 2, right?
N times.
The one after will be 5, 4, 3, and then the 2 is going to fall down before we get there. And so there should be just an n factorial in front of everything. So in other words, our c sub n's are just the nth derivative over n factorial. Does that make sense? So if a function has a series, a Taylor series behind it, the c sub n's have to have this form. Okay? So let's try to, well, let me state it as the formal definition here. So, Taylor and Maclaurin series. I think that's how you spell Maclaurin. Okay, so let me just say Taylor series. Now again, I'm not going to write out every detail of these definitions, but the point is that when we define these things, I'm assuming all of the derivatives exist. So all the functions we're looking at here, your Taylor series, your Maclaurin series, only are defined, right, if every derivative exists. So you can't have a function where you get weird stuff happening with its derivative. Okay? And so, let me just do this. So the Taylor series is, so what we were looking at over there was the Maclaurin series. And the only difference is that the Maclaurin series, you're only allowing your A, the place you're centered at, to be 0, right? And that's how we were splitting that one up. But you can guess that the same stuff works if you're centered at A, but you just replace the 0 with A. And then rather than x to the n, you have x minus a to the n. And everything we did before, that same formula will work out. You just pop A's in there. So this is the formula for a Taylor series. And so, given an f, this is its Taylor series. This may not be defined. Right? Even if the derivatives exist, you might have something that's, doesn't converge. But if you have a convergent, but if this converges, then it'll equal your function. And then the Maclaurin series. And I'll just put here in parentheses, this is just Taylor with A equal to 0. And so a Maclaurin series is a Taylor series, right? And then some Taylor series, in particular the ones with A equal to 0, are Maclaurin series. So most of the time we ask for the Maclaurin just because they're simpler looking, but we could ask for anything here. And so again, this is just this. Okay. So with this in hand, we're going to start to try to build some series for other functions. So find the Maclaurin series for following. We could already have done this one based off some earlier stuff, but let's look at it again. Okay, so let's look at f of x equal to e to the 2x. So if you remember, 3 sections ago, I guess it was 2 sections ago, we said that we came up with a formula for the series for e to the x, right? And it was 1 plus x squared over 2 factorial, x cubed over 3 factorial. So we could just plug the 2x into that formula and see what it equals. But let's find the Maclaurin series just using this formula, okay? So again, it's just going to depend on all the derivatives of your f. And so I'm just going to do this. What's f of 0? Or, actually, let me, now that you say that, let me do it like this. Let me just do this in columns. So f of 0 is 1, right? And so that's what c of 0 is, right? Is just whatever we saw, well, I erased it, but we saw that's what it would be. What's the first derivative?
2,
So 8
2x.
So what's the first derivative at 0?
2.
2. C1 is, and I'll just write it out, it's the derivative over, just to follow that formula, over 1 factorial, right? It's just the derivative though. So this is
2.
2. Second derivative,
4e x.
that's good. So 4 is fine. I'm going to write it as 2 squared. And so your second derivative at 0 is 4, or 2 squared, right? And your C2 is just your second derivative divided by 2 factorial. And so you could make it 2, but I'm going to just keep writing them as 2 squared over 2 factorial. Just leave them in sort of the messy form, because we're looking for a pattern, right? And so if you start simplifying things, you might sort of lose your pattern that was there. So what about the third? Well, do the third and fourth derivative. Play the same game and see if you can come up with it. And if you get finished with that, then start working on sine. See if you can come up with a series for sine. So hopefully you came up with this. And again, this is why you really want to be careful that you don't start trying to cancel things out, because when you get even to the next one, 2 to the 4th over 4 factorial, right, you'd be able to cancel a bunch of 2's out from the top and the bottom, and then your numbers would sort of fly all over the place. Whereas if you leave them in this form, right, it's 2 squared over 2 factorial, 2 cubed over 3 factorial, 2 to the 4th over 4 factorial. If you do a few more, so if you don't see it here, do a few more, and hopefully that pattern just jumps out at you. And that's why I would recommend you don't start simplifying things because it becomes hard to notice the pattern when you do that. And so what we end up with is then the Maclaurin series is, so I'm just going to work my way across. It's 1 plus C sub 1, well, let me just do this. It's C0 plus C1x, right? Plus C2x squared, C3x cubed, and so on. So it's 1 plus 2x plus 2 squared over 2 factorial x squared, right? 2 cubed over 3 factorial x cubed, and so on. Okay?
Yeah.
And if we wanted to write this in our sum form, right, so it's always got to be x to the n. What's the coefficient in front of there? Just the c sub n, right? So 2 to the n over n factorial. So this is sort of the nice closed form. Okay? And so I decided not to emphasize when these actually converge and when they don't. Let's do this for this though. So this is going to turn out to be true for all x. Okay? But let's just look at the radius of convergence of this series. Okay? So if I have that, if I just gave you that series, so you're done with this problem. This is the Maclaurin series. It may or may not converge, but this is it. Okay? So what's the radius of convergence of this guy? Right? So I do my ratio test, right? What would I do for that? 2 to the n plus 1, x to the n plus 1 over
n plus 1 factorial.
factorial, n factorial, 2 to the n, x to the n, right? So same kind of stuff that keeps happening. So I really just end up with 2x over n plus 1. What's that limit?
1/2.
No.
Or the
0, right? The 2x are fixed,
Yeah.
and then over n plus 1. So as n goes out to infinity, the whole thing will go to 0. So your radius turns out to be infinite, right? And so this isn't exactly the formal way you really need to worry about. Well, you gotta look at Taylor's inequality, but this just says that, essentially it says that this Maclaurin series is nice and well defined. I'm being a little bit lazy, but I don't think we have time to get into to get too bogged down. I just want us to realize that's gonna be the right series. Okay, so let's move on to the next one. I said do sine. Did anybody start it yet? Working on sine or no? Okay, let's change our minds then. Let's find the series for cosine. I just noticed the book does sine, so we'll do one that's just a little different. Okay. So try this same thing. Make up this little chart here with cosine now in place, and it's again at 0, and see what you come up with. So this one, I think, it might be rather difficult to explicitly state what the formula for C sub n is, but maybe get the first, recognize the pattern and then we'll talk about it. There's gonna be a bunch of zeros in there that'll throw off your formula. All right, so let's work our way through this together. So what's f of 0? 1, c of 0 is then 1, right? So you got 1 and 1, and again, you should eventually get this pattern, but let's just take our time. What's the first derivative?
Negative sign.
Negative sign, so you plug in 0. 0, right? And then, so c sub 1 is 0, well, I just write it as 0.
0.
0 over 1 factorial, right? Second derivative is negative cosine, so I get negative 1, right? And then your c sub 2 is negative 1 over 2, I'm gonna write 2 factorial. And then keep working our way down. Third derivative is back to right now to positive sign, which is 0. So c sub 3 is 0, but again, 0 over 3 factorial, so you get another 0, right? How about the fourth derivative? You're back to cosine, right? And so that's 1 over
4 factorial.
4 factorial. So without worrying about derivatives, this pattern now should just repeat, right? Because it's just going to flip back between sines and cosines. So you get 1, 0, negative 1, 0. So 0, 1, or sorry, negative 1, 0, 1, right? And so on. And so over here, 0 over 5 factorial minus 1 over 6 factorial, 0 over 7 factorial, positive 1 over 8 factorial, and so on, right? So the point is, you skip all the even term, or sorry, odd terms, right? And then your sign flips on the odd, or on every other even term, but it's the same, just 1 over factorial with the sign flipping, right? So let's write it out real quick. So I get 1, and then I get no x's, right? 1 plus 0x plus, or actually minus 1 over 2 factorial x squared plus 0x cubed. What's next then? Plus 1 over 4 factorial. Plus 1 over 4 factorial x to the 4th. Plus 0x to the 5th, right? And then minus 1 over 6 factorial x to the 6th. And that pattern repeats. Now, when we write this out in practice, we don't want to bother putting the 0x, right? The 0x cubed would drop those off. So this is the series you want to think of. 1 minus, all right, this way, x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on, right? Just alternating like that. So let's come up with a closed form for this now, a summation form here. So the first thing I'm going to deal with is that I have that sign that alternates plus minus plus minus. So how do I get that in a sum?
Negative 1 versus.
Yeah, and so does the n work, or do I need n plus 1?
Plus 1.
No,
So when n is 0, I get positive, right? Is that what I want?
yeah.
Oh,
Yes, right? So the n's fine. If it was wrong, then you just put in n plus 1. But that's good. Does that make sense though? Okay, now how do we just make sure we only get the even terms?
Put in a,
2x plus
2 n.
We add 1.
Right, so let me just write this. So, well, we're starting with 0, right? 0 is 2 times 0, 1 is 2 times 0 plus 2 times 0 plus 1, right? 2 is 2 times 1, 3 is 2 times 1 plus 1, right? And so all the evens just can be represented by 2 times something, right? That's what it means to be even, and all the odds by 2 times something plus 1. So we just want the evens this time, but I can just say that's x to the 2n. That'll run through just the evens. And then how does my denominator compare with my power?
2 times n.
Okay.
Factorial.
Good, and it should be this though, right? The 2n first, right? 2, 4, 6 factorial. So you want to make sure you're not doing n factorial and then multiplying by 2. You're taking the factorial of the whole power. So whatever that power is should match up exactly. Does that make sense or not? Okay. Okay. And so I didn't show this, but I'm just going to say this. This works for every x as well. Okay, so what function was this? Cosine, right? So cosine of x, the series for it is this, and it's true for all x. Okay. All right, so you can do this in a couple different ways, but here's what I want us to do. How would you find a series for sine? Well, you could mimic what we just did, right? You could do the same thing. It'll be almost the exact same work, right? It'll be 0, 1, 0, -1, and you'll get that same pattern. But the previous section, or 2 sections ago, we said that if you knew a series for a function, you could take its derivative and you'd get a series for the derivative, right? You took a derivative of the series term by term. And so we know cosine of x is this sum, right? So now if I just differentiate, what do I get? What's the derivative of cosine? Negative sign. So I'll have to deal with that, but that's close to what I want, right? And then what's the derivative on the right-hand side? Oh, be careful here. So the -1 and the 2n factorial will just sit there, right? And so your exponent will follow. And actually, you know what? I think I want to do it this way. Here, let me do it this way. This is fine, but let's also think of this as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. Let's do the derivative with this form, just so we see what's happening. So you take the derivative of that other form, right? The derivative of 1 is 0. The 2 falls down, and so you just get minus x plus the 4 falls down, and you get what? Over 3 factorial, does that make sense? And then, I didn't write it up here, but the next one would be x to the 6th, right? The sign's going to alternate. The 6 will fall down. You'll get 6x to the 5th over 6 factorial, but the so it'll cancel and you get that. And then you can probably guess the pattern. What should be the next guy?
X to the 7th.
7 over 7 factorial. And then it'll be minus and so on, right? So we didn't want negative sign, we wanted sign. So I just negate everything. the same pattern, except for here we've picked off just the odd terms instead of the evens, right, with sign. And as long as we're here, let's do this again. Sum from 0 to infinity. Again, it starts positive, so I'll just make it -1 to the n. That'll make my sign flip. And now I want just the odd powers. And I guess I erased it, I had it up over here. How do I get just the odd powers? Yeah, if 2n, not just n plus 1, but 2n plus 1, right? 2n gives me the evens, so 2n plus 1 gives me the odds. 2x to the 2n plus 1, and then whatever that exponent is on the x, 3, I want 3 factorial, 5 factorial, right? So I just take that exponent, 2n plus 1, and I take the factorial of the whole thing. That make sense? And since our cosine formula was valid for all x, our sine formula will be as well. And I'll mention one more time, right? The validity of these for all x, I'm waving my hands at it, I'm showing you why that's true, but they spend a little time on it in the book, I just think we don't have time to devote to it in the summer here. Okay. So, any questions on this so far? So there'll be a table, I think it's on page, well, let me just find it, 775 in your book. That's what I wrote down. That has a list of the Maclaurin series that you eventually want to memorize. So eventually this one needs to be memorized, so does cosine, so that you can make use of it. But we'll come back to that in a minute. Let's do one more series here. So find a Taylor series for what do I pick? It's just so hard to decide. There's so many fun and exciting functions. Let's just do log of x, okay? And then we'll do it at or around x equals, well, I'll just say at x equals 1, okay? So, and maybe I'll say a. So we're going to use a equals 1, so we'll use that formula for the Taylor series now. And so let me just mention, right, the Taylor series is going to be this then. F of a plus f prime of a times not x, but x minus a, second derivative of a over 2 factorial times x minus a squared, and so on, right? So we want to do exactly the same thing we did, we just want to be careful when we write it out, it'll be x minus 1 instead of x. And then we'll plug in 1 into our function each time. So it's the same idea. Right, this time we're plugging 1 in, what do we get? F of 1? 0. And so your C0 is 0, right? So this one will take a little bit of work, but see what you can come up with. Start taking derivatives, see what those look like, and then see if you can come up with a pattern. So this one, the derivatives get a little bit uglier, you gotta be a little bit more careful. Problem is, the first two aren't so bad, and then you'll get led to the wrong pattern. this through if you haven't gotten them there. So, right, your derivatives, just be careful if you don't see those, right, just write them as x to a power. This is x, so negative x to the, well, x to the negative 1, right? So then negative x to the negative 2, and then the negative 2 falls down, so you get 2x to the negative 3, and then so on. And if you do enough of them, I think up till 5, you start seeing a factorial pattern arising here, right? 4, 3, 2. The next one, it'll be a negative 5, 4, 3, 2. So it's factorial, but then the sign's also flipping, right? And so you come up with this, I think C sub 5 will give you, right, 4, 3, 2 up top, right? The fifth derivative, and then divided by 5 factorial. And so let's just work these out. We get 1, negative 1/2. So this time, you could write it in the ugly form, but a lot of stuff cancels, right? So what happens here? I just get 1/3. Here I just get minus 1/4. Does that make sense? And here I get 1/5. So it looks, and I think you should be able to convince yourself that same stuff's going to keep happening, right? Sign's going to flip, and then you'll keep getting an extra or number in front of there, an extra coefficient, so you'll get that factorial. And so what should C sub n be? So you want the sign to flip, right? Okay, let's do this first, and then what's on the bottom? Well, be careful, it should be C sub 4 has a 4, C sub 5. So you want n down here, and then you don't want negative 1 to the n, right? Because if you did that, then when you plug in 1, you'll get negative 1, right? And when you plug in 2, you'd get positive 1/2. So it should be n plus 1. Does that make sense? And so our Taylor series looks like this. So our series is 0, right, plus 1x, not just x, but what, x. We're centered at 1 this time, right? So x minus 1 minus 1/2, x minus 1 squared plus 1/3, x minus 1 cubed, and so on. And so in the closed form, the easiest thing to do here is probably ignore the 0, right? You could include it, it probably works out fine, but it's really natural to start at 1 instead, right? And then what's our pattern? Or it's negative 1 to the n plus 1 over n times x minus 1 to the n, right? Does that make sense? And I'm not going to bother with this. This one won't work for all n. This is only going to be defined for, well, appropriate x. And again, I'm going to wave my hands at it a little bit. It'll really be, well, x should be between 0 and 2 for this to make sense. But let's not worry about it. This is the Taylor series for that guy. Does that make sense? Okay. So, computers have become really powerful nowadays. And so they can deal with things. Like even back when I was in college, I guess it was starting to be okay when I was in college, but you didn't have, nobody had ready access to things that could just find the derivative of a crazy function like, you know, Wolfram Alpha can or something else. And so a lot of this stuff, like if you talk to an old engineer, right, and you ask them what's sine of x, or how do you deal with sine of x, they don't say you plug sine of x into a computer. They say, oh, well, sine is this guy. And they'll just use this polynomial instead of the whole sine, right? They won't even use the whole series. They'll just truncate it there. And for almost all applications, that's going to be close enough to sine that everything works out just fine. Okay? And so it's still a really valuable thing, because even though computers have gotten really powerful, dealing with a polynomial just involves multiplying and dividing, right? Just basic arithmetic, which the computer can do much quicker than it can trying to evaluate a trig function. So it's still a valuable, racing and writing at the same time. I should learn how to do that, guys. I already put my next line up. So these things so computers, even though they're really powerful, it's still valuable to be able to approximate functions by things. And so the Taylor polynomial of the function is just the truncated series, right? So your series, so your f of x, its series, I'll just write it like this, is f0, or sorry, fa, f prime of a, x minus a, second derivative at a over 2 factorial, x minus a squared, and so on. And again, the pattern, or the formula is just right, the nth derivative at a over n factorial, x minus a to the n. So the Taylor polynomials, let's start with T1. So the first Taylor polynomial is just take the first degree polynomial and drop off the rest of it, right? So it's f of a plus f prime of a times x minus a. And if you remember back to calculus, this is just the linearization of a function. This is the definition of the tangent line of a function at a. And so the idea was that you could approximate a function using a straight line, right? And so that works as long as you stay really close to your a. So the rest of the Taylor polynomials just say, well, let's do one better, right? If a straight line approximates some curve, maybe a quadratic does a little bit better job. And so you just build it up like this. Does that make sense? And then a third degree and so on. And so I'll write it up here. In general, then the nth Taylor polynomial, t sub n of x, for this is, again, all with some f in mind, is just, right, f of a, f prime of a, x minus a, and then you just work your way down to the nth derivative over n factorial, and x minus a to the n. Does that make sense? So you can always do these things. And so all I want to do today, I don't want to spend a whole lot of time, but the point is that you can control how good of an approximation these are using the error stuff. And again, I'm going to skip the error because it's just a messy calculations, but you should at least know in the back of your mind, I can always kind of get control of how bad my error is, how far off I am. And so let's just use the formula we came up with for sine. So sine was x minus, I'm just going to repeat what I had just said, x cubed over 3 factorial, right? Plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And so the Taylor polynomials here are just x, what's t sub 2? It's sort of a trick question.
So whatever x?
No, it's still just x. It's x plus 0x squareds, right? So it's x as well. So we're just going to grab the odd one. T sub 3 x minus x cubed over 3, right? T sub 5 x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And let me just say, so in some, I mean, I guess it's in a real way, but the point of doing these is your linearization was saying, take f of a, right? You start at the same point as your function, and then you have the same slope as your function. The second Taylor polynomial says, well, let's do one better. Let's assume we start at the same point, we have the same slope, and we have the same second derivative as our function. Right? The third says your first, second, and third derivatives all agree at that point. And so you should imagine that you're getting better and better approximations of your curve as you do this. And so you don't have to worry about recreating a bunch of this, but I just wanted to show you with one real simple example. So here's sine. Does that look okay on it? Should I
You
turn
can-
off lights or?
You can kind of see it.
All right, let's turn off lights just to be safe. So, there's sine of x. Again, its first Taylor polynomial is just x, right? And this is the Taylor polynomial at 0, right? So the Maclaurin, sometimes you call them Maclaurin polynomials. I'm just going to keep calling them Taylor polynomials. So y equals x is just a straight line, right? That goes through here, and so it has that same slope. And so here's y equals x. I plot that. See? And you just get that straight line going through. And so that's a great approximation as long as you stay really close to 0, right? It looks pretty close, but then obviously it falls away. And so the third Taylor polynomial just says, let's try to approximate this using a cubic. And so what do cubic functions look like? Like that, right? Or the other way around. And so it seems like that might give us a better shape, right? The cubic might do a better job. And so now let's just do that. We add in the minus x cubed divided by 3, well, divided by 6, right? So we get that, and let's plot that guy. And that, now that one stays pretty close looking until you get way over here, right? And then if you think now maybe look at the 5th degree polynomial, that might even do a better job of approximating your curve. And so put that in. So plus x to the 5th divided by 5 factorial. All right, and now you can see that does a great job all the way to the top of that next hump, right? And then minus x to the 7th over, I don't know if I probably don't need these parentheses. Over 7 factorial, again, that should do an even better job, right? It's going to stop being, at some point we're going to fail to, to get stuff until you take a big power. But the idea is now, right, we're staying pretty close to x till almost 2.5, right? You wouldn't have to do too many more before you'd be accurate for sine of x up to pi. And that's about as accurate as you ever need to be, right? Because you can grab all the values between there. Does that make sense? And so we're not going to do a ton of it, but just the idea that, hey, look, these complicated, ugly functions can be approximated pretty quickly by simple polynomials is an important idea. Make sense? Okay. Well, let's stop there for 12.9 then.